Hello everyone and welcome. This is a summary YouTube video about the heavy lift drone design. This is a heavy lift drone for the military. I'm happy you're here and I welcome you, and I suggest, if you want, subscribe to my YouTube channel. The name of my YouTube channel is Patrick Gray. There's a lot of fun stuff there. We're looking at right now Capitol Reef National Park in Utah. I do cover my thoughts about the heavy lift drone in a series of YouTubes on my YouTube channel in more detail. This is a summary YouTube. I also discuss my thoughts about this as a page on my website, and here is my website. And you can see that I talk about a lot of things. Hello to everyone. There is a robot discussion, but the heavy lift drone is not about a robot. So you click here, and then down here is heavy lift drone. I do have a PDF that I created that goes over all of the technical data. You can download that PDF and see what I'm talking about as a PDF file. All right, I do like to add this. This is a discussion YouTube and a discussion website. Any physically real object could potentially act in a manner that is dangerous, either hurting people or hurting equipment. Any physically real object should be managed in a way where this management of it is reasonable and safe and also legally allowed. And my advice is, if you cannot manage a physically real item in a manner that is reasonable and safe and legally allowed, my suggestion is don't create it as a physically real item. Here is a heavy lift drone design that I created. This is a drone that sits on the ground with its legs. I wanted the legs to have that triangular attachment, 1, 2, 3, for stability. Separate legs so that it could land on an irregular surface, and when it takes off, it folds up its legs and it flies off in a horizontal configuration. And the question that I started with was, why doesn't the military have a heavy lift drone? Why do they not have one? That seemed to me like, what's wrong here? I think a military heavy lift drone could have 4 functions. One is picking up and moving around materials. Pick them up, carry them somewhere, put them down. Picking up and delivering ammunition. Picking up and delivering human beings, human soldiers, including medical flights. A 4th job for a military drone would be to pick up or have on board the drone a weapon system where the drone brings the weapon system up in the air, takes itself to an area of battle, and the weapon system sends kinetic output down to enemy forces on the ground. And all of that seems to me like something the military would want, and it's strange that they don't have it. And I thought, well, what is going on here? My feeling is that somehow the military they have to have this as being an electric device. And an electric device is not currently practically feasible for a military heavy lift drone, because the military heavy lift drone is going to have some features that are special to the military. One is that needs to be robust. It needs to work. When they turn it on, it works, and when they turn it off, it doesn't. But it also needs to have a significant payload. It needs to have a non-fuel payload of up to 1,000 pounds and a fuel payload up to 600 pounds. It needs to have a range. It needs to be able to fly 200 or 300 miles. And I'm not sure that it really needs to be pretty or sleek or eye-catching. If this drone arrives with ammunition and saves a group of soldiers, I don't think they're going to care what it looks like. If they're in serious trouble, it arrives, they get on it and leave, or it arrives with a weapon and turns the battle in their favor. I don't think the soldiers are going to look at the drone and say, well, we didn't really want to be saved by that drone because it's ugly. I don't think they're going to say to their commanding officer, don't send the drone to save us because the drone is not electric. If it's not electric, we don't want to be saved. I just don't think they care. And I don't know, I think the military needs to consider creating a drone that's not based on electric at present because it's not feasible for a military drone. And I thought, well, where is the power that's going to be able to run a military drone if not electric? And in my opinion, the answer is the turboshaft jet engines for helicopters. These engines have many advantages, one of which they're already created, they're already optimized, they're already certified for flying, including flying with human beings on board. And the power ranges go from 300 horsepower up to 8,000 horsepower. So whatever amount of horsepower you need, you can get it. And so why not use them? The other issue, I think you can see this, has wings. When you take a device, a flying device, and bring it into the air with its propellers, that can be done. And it has a gigantic advantage that you don't need a runway, which is a really big deal, not to be dismissed lightly. But the efficiency of lift with propellers, the efficiency of lift of an airfoil is related to the size of it. So as it gets bigger, it's more efficient. And a drone that can keep itself in the air on its wings uses about 1/5 as much power for that amount of support versus a drone that has itself up in the air because of its propellers. This means all of the big heavy lift military drones are going to convert to fixed wing flying as soon as they can. And that's why I put wings on the drone. This is an image of the little drone. That's 44 feet. The cargo carrying capability of this drone, this is about 4 feet by 4 feet by 3 feet. It has a 300 horsepower Rolls-Royce turboshaft jet engine. The jet engine is running a series of bent axis hydraulic pumps, and these pumps are sending pressurized fluid to bent axis hydraulic motors that turn the propellers. You can see that the propellers are what I call fat cord propellers. These are optimized for lift at 0 airspeed. And one thing that's interesting about this in terms of flying by fixed wing, where these propellers are not turning and you're just dragging them through the air, for true heavy lift drones, this is so much air resistance that it's not going to be feasible. Now, this drone solves that by going up in the air and turning itself into horizontal flight. And that way the propellers that were providing vertical thrust also begin to provide horizontal thrust. And this drone, it's very important if you want to have the nose up, tail down, take off and land situation. You can't have a horizontal stabilizer sticking out of the back end of the drone. I solved this problem by making the fuselage of the drone is an airfoil. It's actually upside down and backwards. But what happens is the airfoil of this fuselage creates a positive moment on the drone, and that positive moment interacts or counteracts the negative moment created by the wings. And so the drone has stable flight, but it doesn't have a long tail sticking out the back of it. It's my opinion with these heavy lift drones, it's only a matter of time before they make them carry human beings. And this is the big version of that drone where the fuselage has been expanded. I think this is 14 feet. We have 2 people inside it, dual 300 horsepower Rolls-Royce engines. And I have an extensive math analysis. This is not hard to figure out. You take the weight of this drone and its payload of 500 pounds and 500 pounds of fuel, and take all that weight and divide it by 6, and that's the thrust that this propeller has to create, and you just figure out if the propeller can do it, and it can. So this drone will be able to go right up into the air, and then it will cruise along at 70 or 80 miles per hour for 7 or 8 hours. And this is a drone that I think might be used to provide electronic countermeasures. I believe what's going to happen with big military heavy lift drones is they're always going to be in pairs. One will be the big person, the big drone that's doing all the military work, and the other will be the little drone that has electronic countermeasures in it. And the little drone flies along with this drone and protects it. The little drone won't have a human being inside, and the big one will. And I have an extensive math analysis that shows these turboshaft jet engines clearly can make enough torque and RPM to run these hydraulic pumps. And these pumps can feed these hydraulic bent axis hydraulic motors. And the Parker-Hannifin bent axis motors have a radial axial stabilized roller thrust bearing in them, so the motor itself can be directly mounted to the propeller. Now, I think an issue is going to happen when you put human beings inside of a drone. My story is stable hover is critical for a drone. You'll spend 95% of your time trying to get stable hover. Once you put a human being in the drone, you're going to take everything you were worried about, and it will be switched into being worried about these people. So instead of 95% of your time on stable hover, 95% of your time on this one will be protecting these people inside. And all the rest of what you were worried about with the drone will be condensed down into 5%. That's just how it is when human beings are involved. And here I'm going to go over a couple of topics very quickly. All of this is covered in more detail in my other YouTubes. A human being cannot successfully fly a drone. Human beings cannot adjust the RPM of these propellers precisely and rapidly enough to keep it in a stable hover. They can't do the calculations. What they discovered with drones is you have sensors on the drone that say how it's oriented. Those results go to the central processing unit. The central processing unit decides what it wants to do and sends modulation commands to a output device which tells the motors what to do. And this loop goes around and around like this. It refreshes itself 10 to 50 times a second. And human beings, while they might think that they're flying the drone, they're not. The human beings tell the CPU what they would like the drone to do, and the CPU works the human suggestions into this loop so that it looks to the human like he's telling the drone, but he's not. And this is very important to understand, because what that means is you don't need a fairly highly trained, sophisticated military, full-fledged pilot to fly a drone, because the drone is flying the drone. And this allows you to take these drones and send them out to an isolated small outpost, 3 or 4 of them, There's no pilot involved. The people who fly them are members of the outpost. The drones are under the control of the commanding officer of the outpost. So his drones under his control are 8 to 12 miles from his people who are out on patrol. And when he wants to help them, he just turns the drone on and helps them. He doesn't have to talk to Central Command or wait for available air or anything like that. And this is totally different from how current aviation works for military support. And again, all of this is carefully explained by me and shown by math to be totally feasible. This is the schematic portrayal of how this works. The turboshaft jet engine, this is an Allison 250 designed by Rolls-Royce, turns gears that turn these pumps. The output of the pump goes through a flow control valve. This is controlling the output. That output goes to the bent axis hydraulic motor, and the return from the motor goes back to the pump. So this is the output of the pump. This is the input of the pump. And you have enough pumps here that you can run all 6 propellers. And there is a ball nut system here run by a servo motor. This servo motor adjusts this shaft, and when that shaft is adjusted up and down, it controls the flow. And this is a hole that goes from this end of this control to that end. So there's no differential of pressure from here to here. And there's no differential of pressure from here to here. So this moves easily. And what you're doing is modulating the output of the propeller to get stable hover and stable control. And you can see this is a manifold that would run 6 of these. Common input, let's see, inputs down here. So common input, common output. And I wanted to mention here I made a 3D drawing of the CTS 800. This is about a 1,000 horsepower turboshaft jet engine, which is what we'll need for the next concept. But there it is, and it exists, and you can get its specifications. It's my opinion right now, heavy lift drones are in their infancy. It's very early. And if you put human beings in them, you must keep it safe for the human beings. And the truth of drones is catastrophic loss of power. The only thing holding you up is these 6 propellers. If you have catastrophic loss of power, you're on your way to the ground and it's over. And I don't think that should be done. I think what should be done until they get drone concepts really stable and well known, put the VTOL drone equipment on a completely functional airplane so that in the event of a catastrophic loss of power, the pilot can just land the airplane. And remember I said we don't need fully qualified pilots, but we will need them for a while as we figure out how to make these drones work. This is the CTS 800 1,000 horsepower jet. Of interest, you can see that it is providing pressurized hydraulic fluid to these pumps. And these pumps are sending the pressurized hydraulic fluid to these bent axis motors. And so the truth of these jet engines is they can be located wherever you want to locate them on this plane. And this is the DHC-2 plane that is a bush pilot plane for use in unimproved airfields or airfields that don't even exist. Because, of course, if you lose your power, you're probably going to lose it when you're not over a totally functional runway. And of interest with these planes, if they are not maintained or are not optimized to have their certification for flying human beings, then the planes become available for sale at a much lower price because you can't use them for human beings. But you could definitely use them to create the addition of this drone vertical takeoff and landing equipment and get the plane optimized in a more inexpensive fashion. Again, I think this plane is going to need to fly with tilt rotor. So this is a VTOL where these propellers are optimized. This is a hinge mechanism run by cylinders. So the propellers are pushing down. This is a pusher propeller, that's a pulling propeller, and it goes straight up in the air, and then these devices begin to rotate under the influence of these pistons that take this crank and tilt the entire structure over so that eventually the motors are oriented in a horizontal thrust configuration. You see this has been lifted all the way up, and it flies along this way as a fixed wing flying device. This particular drone can carry 1,000 pounds of non-fuel weight, 600 pounds of fuel weight. It can go to 500 feet in the air in 30 seconds using 8 pounds of fuel, and it can fly at 125 miles an hour using 136 pounds of fuel per hour. So it has a range of 450 miles and go up in the air, switch to fixed wing, fly. Well, if it's going to fly there and back, it goes up, flies 200 miles and lands itself, goes back up in the air, flies 200 miles and lands itself. All of this is doable at any point if they have a catastrophic loss of power. They just land it as a glider, and I can show this with math. I do have a device that I call the Smart Mortar. It's a gliding device. It doesn't have a motor in it. It has a 4-pound C4 shape charge warhead. I have an extensive discussion of how this warhead works. I wanted to make a warhead that can be used on any target. I don't want commanding officers to have to swap out the warhead depending upon what they're trying to do with it. So I designed a warhead that works for anything, and that is in my YouTube videos. But these weigh about 40 pounds, and this plane can carry 12 of them. And this is just a different view. This plane would probably go up with 2 people, one person running the controls to fly it, and another person basically picking up one of these, taking it down here, and launching it. And here you can see one of the smart motors has been launched. There's the flight control surfaces. This is about 40 inches and this is about 36 inches. It has a glide ratio of 4:1. So if this is at, say, 10,000 feet in the air, then this can fly for 40,000 feet. So that's 8 miles. So this could be released 8 miles from the target area. And this would be a glider. It won't make any sound at all. And it can fly along and then point it. It flies at 70 miles. It has, the stall speed is 60 miles an hour. It flies at 70 miles per hour. It puts its nose down. It will hit the target going 100 to 150 miles an hour. I don't think they would even see it. And they wouldn't hear it. And I'm not sure if this couldn't be carbon fiber, which means they're not going to be able to see it with radar. It's just going to, all of a sudden, there's going to be an explosion. And the enemy forces will be saying, what just happened? Where did that come from? And this is extensively discussed, including math. And it's another set of YouTube videos that I made. On here, I showed the inside of it. This is a little mannequin I created. He's 6 feet tall, has the proportions of a human. I put fans in here so that this could fly at its stall speed, and if it managed to get itself into an irreversible stall, it could spin up these fans and blow air out through its flight control surfaces area and force itself from an irreversible stall back into controlled flight. And that was in order to be able to let it fly along at its stall speed. And here is that warhead again. That's extensively discussed in my YouTubes. I did want to address the fact that the jet engine running the drone will have its output at full output for VTOL, but its output will be 1/5 of its power output for fixed wing flying. And it's hard to optimize a jet that can have a power output that's efficient at 1 and then have the same efficiency of power output at 1/5 that amount of power. And I was considering addition of a propeller at the intake of the jet, and when the jet powers itself down to its 1/5 power setting for fixed wing flying, a hydraulic bent axis hydraulic motor here spins up this propeller and forces intake air into the jet in excess of what the intake would be just from the fixed wing flying speed. And what happens is, I'm hoping is, you can have the jet with the same efficiency of power output per pounds of fuel burned when it's going under full power at 800 to 900 horsepower, get that same efficiency of fuel burning when it's putting out 110 to 120 horsepower, because this input fan is optimized for the 800 horsepower output. But if you force air into it and pressurize the intake, that same centrifugal fan might be able, I don't know, I hope it would work. It might be able to bring the efficiency up even though the output of the jet engine is down in the 120 horsepower range. That needs to be investigated. Of note, in my opinion, you can test these propellers. There's the bent axis motor and the propeller. This is a pressure force gauge with a bearing. Over here is a 2,000 horsepower diesel motor. These don't have to be powered by the jet engine when you're testing them. And you can run the tubing over here and get your RPM versus thrust values for this propeller in a static system to establish that you know it will work. And you can also interpose in here the thrust control modulations manifold that I showed you to prove that you have proper control of this propeller. And this is all discussed in one of my YouTubes. And I wanted to show that you could make a little baby drone, 6 propellers on a frame, where this frame is captured inside of this restraining structure so it can't do something crazy. But you could put sandbags on this and bring it up to 4,000 or 5,000 pounds of weight, put this 2,000 horsepower diesel engine on here, and optimize the hover and control of this device without ever having to create an $80,000 drone. And if you were wrong, you can tell your programmers, folks, try again. But you didn't destroy anything because this capture frame here won't let it. And this is a way to test it. Another concept I wanted to bring out was taking this propeller and putting it on a flatbed trailer with the diesel engine here so that you can measure the thrust output of this propeller as the airspeed changes, so that you don't have to have it flying around in a flying device. In addition, you can take this from the seashore up into the mountains and get the thrust of this device as a function of altitude without it ever having to fly. And you can also orient it, again, I think this has that little force sensor here and the bearing, and so this thrust is measured, but this is all anchored. But you could also turn it and get values for how this propeller, the thrust of this propeller is related to the sideways motion of the drone. And this is all discussed in my YouTubes. I wanted to quickly mention that I created a test stand where these are ball glides. They have a lot of names. They're used in the airport industry for rolling around the containers. But what you can do is, these are cardanic joints connected to the drone. These cardanic joints have hydraulic cylinders in them. So if you free float the cylinders, okay, this can move this way by 30 inches, and it can move this way by 30 inches. And this can go up and down 4 or 5 inches, and you can get 30 degrees of tilt on this drone with these cardanic joints. at any point, if your programmers were being brave, innovative, and exciting, but wrong, and this thing wanted to crash, you lock up the fluid flow on these hydraulic cylinders and it grabs the drone and won't let it move. And so you didn't crash it. And so you have an $80,000 drone. Your programming was wrong. Everybody feels bad, but they just turn everything off and start again tomorrow because it didn't crash. Because this, which was allowing it free motion, stopped it. And so that's something, that's all discussed also. I suppose I'll finish with the fun stuff. Here's the little mannequins. Here's the big guy that's, I think, qualified for human flight. Here's the little one. That would be the electronic countermeasures. This is Gunnison, Colorado. And they're out just flying around, having some fun. There's those two CTS 800 jets. What fun. Interestingly enough, I went to Montrose Airport. I think it's back over in Colorado. This is about 8 or 9 miles. But what I wanted to do was take this drone with human beings on board and let this drone do, this is, I think, like 5,000 feet altitude, and this is 13,000 feet altitude. So you can do an 8,000 foot climb. Here's the track. With this drone, where the drone is never more than 8 or 12 feet off the ground. So if something goes wrong while you're proving that this drone will work, you're only 12 feet off the ground. But you went from 5,000 feet to 13,000 feet. And I don't know if you know military pilots, but in my opinion, somewhere down in here is around 9,000 feet. They would take this drone and they would fly it up here and come around the corner and land it right here. I call this the crow's nest. And those military pilots would be like, that's what we're going to do, and you can't make us not do it. I think, I don't know. You know, you just have to understand pilots. And the other thing, just for fun, this is the Black Canyon. It's got a name. It's near Montrose Regional Airport. And you know that these pilots, you'd be telling them, you don't go down in the valley with this plane because we're not quite sure about it. And they would park it and say, oh, come on, let us. We'll fly it right down here. It's a VTOL plane. It doesn't need a runway. This is the whole point of this thing. And we'll put it right here. And we promise everything will be cool. We'll get out, put our feet in the water, we'll get back in the plane, and we'll fly it straight up out of this valley and land it over here. If you guys will just quit paying attention to us for about an hour, we'll do this. And of course, I don't know. I just thought that would be fun. This is all imagery obtained through Google Earth. Anyway, that's the update. I have more going. I was working on a valve control system for the tilt rotor, but that's very detailed stuff, and I can get into more of that. All of this is covered in more detail at my website and on my YouTube channels, and I hope you enjoy, and I'll get another update going when I get a chance. Thanks again, everybody. And oh, by the way, have a happy holiday. Let's hope next year is a wonderful year with no problems. We can all